Have you ever looked at a massive mountain range, something that weighs billions and billions of tons, and just wondered, how does that not just sink straight into the earth? Well, today we're going to dive into the incredible hidden science that explains it all. It's a principle called isostacy.
So, let's start with a puzzle. On one side, you've got a towering mountain range. On the other, a giant iceberg. Now, at first glance, they seem about as different as you can get, right? But what if I told you they share a fundamental secret?
The answer is so simple it's almost hard to believe, and it might just change the way you see our planet. They both float. Yeah, that's right. Solid rock just floating on a sea of something even denser.
Okay, I know what you're thinking. How in the world can solid rock float? It's a pretty wild idea. So to get our heads around it, let's start with a much simpler picture. One that gets right to the heart of how our planet's crust actually works.
Just imagine you have some wooden blocks in a tub of water. The tall, heavy one. Well, it has to sink down deeper to support its height, right? Meanwhile, the shorter, lighter one just kind of bobs closer to the surface. Each one finds its own sweet spot, its own point of balance. Now, hold on to that thought because it's the key to everything.
So this idea of a natural balancing act, it isn't just a neat little analogy. In geology, it's a fundamental principle that literally governs the ground beneath our feet, and it has a name, isostasy.
The name actually comes from Greek and it means equal standing, which is just perfect. It's this core idea that Earth's entire crust is in a constant state of gravitational balance, literally floating on the much denser mantle below it.
All right, let's swap out our simple analogy for the real deal. Our wooden block? Well, in reality, that's the lithosphere, the rigid, rocky shell of the Earth that we live on. And the water it's floating in? That's the asthenosphere, a super hot, weaker part of the mantle that, over millions of years, actually flows like incredibly thick, gooey honey.
But you know, this whole idea wasn't just figured out overnight. No, it actually started as a huge scientific mystery that stumped some of the brightest minds of the 19th century and forced them to completely rethink the very structure of the Earth. So, picture this. It's the 1850s, and surveyors are mapping the Himalayas. They notice something really weird. They were using a simple plumb line, basically a weight on a string, and the massive gravitational pull of the mountains should have yanked it way off course. But it didn't. It was as if the mountains were somehow hollow, or at least way lighter than they had any right to.
This puzzle kicked off a fascinating scientific debate, with two main theories emerging. In one corner, you had George Airy with his iceberg model, and in the other corner, John Henry Pratt with his wooden block model. Both were trying to solve the exact same problem. What in the world was holding the mountains up? Airy's theory was pretty straightforward. He said the crust is all made of the same stuff. It has a uniform density. So, just like an iceberg where most of the mass is hidden underwater, he argued that a tall mountain must have a deep root plunging down into the mantle to support its massive height. Taller mountain, deeper root. Simple.
But Pratt had a totally different take. He said, no, the crust sinks to the same depth everywhere. In his view, mountains are tall because they're made of lighter, less dense rock, kind of like a block of cork floating next to a heavier block of oak. The lighter rock naturally just floats higher.
So, who won the big debate? Airy or Pratt? Well, here's the really cool part. They were both right. It turns out that Airy's deep roots model is perfect for explaining massive structures, like entire mountain ranges, while Pratt's density model works great for individual features like volcanoes. Okay, so we have the theory, which is fascinating all by itself. But now, let's look at where this incredible principle is actually happening, right now, reshaping our planet on a massive scale.
Remember Airy's theory about mountain roots? Well, it turns out he was absolutely spot on. We've since discovered that major mountain ranges, like the Himalayas, have these enormous roots of crust that extend deep, deep into the mantle, way thicker than the crust under the plains. It's a perfect real-world example of his iceberg model.
But maybe the most mind-blowing example of isostacy in action is something called glacial rebound. Just picture this. During the last ice age, huge parts of the globe were covered by ice sheets that were 2 miles thick. That unbelievable weight literally pushed the Earth's crust down into the mantle. So when the ice finally melted, it was like a giant thumb being lifted off a sponge. The land started to slowly rise back up, and in some places, it is still rising today. In places like Scandinavia and around Hudson Bay in Canada, the land is still rebounding by up to a centimeter every single year. I mean, think about that. Our planet is still adjusting to a weight that was lifted more than 10,000 years ago. That's just incredible.
And that's really the crucial takeaway here. This isn't just something that happened in the distant past. Isostasy shows us that we live on a dynamic, ever-changing planet that is constantly in this subtle state of motion, always seeking that balance.
You can really think of the Earth's crust like a giant, slow-motion seesaw. When a mountain erodes, weight is taken away from one side, and it slowly rises. When a volcano erupts and piles on tons of new lava, weight is added and that side sinks a bit. It is a constant, dynamic dance of equilibrium.
So let's just recap the big ideas real quick. First, Earth's rigid crust floats on the more fluid mantle below. Second, massive things like mountains need deep roots to stay balanced. Third, the crust is dynamic. It rises and falls as huge weights, like ice, are added or taken away. And finally, this whole balancing act, isostasy, is happening all the time, constantly reshaping our world.
And this brings us right up to the present day. We are literally watching this very process unfold in real time as the huge ice sheets in Greenland and Antarctica continue to melt. And it leaves us with a massive question. How will this ancient, powerful balancing act continue to reshape not just our planet's past, but all of our futures?